Hello everyone, welcome to the podium presentation section on the topics of environment and material and human health. My name is Amy and I'm joined here today by Divani, which we're the moderators facilitating this section.
Well, thank you very much. I guess I am going first, so it means I can't lower the bar. So my name is Jilai. So I'd like to welcome all of the guests, fellow presenters, as well as our esteemed judges for the day. And despite, I think, what it says on the scheduling notes, today I'm presenting on the extraction of rare earth elements from a neodymium magnet using supercritical CO2. This summer I've been working with Professor Giselle Azimi in the Department of Chemical Engineering, and I'm very happy to be speaking with you. So I guess we'll jump right into it then. Rare earth elements. At first glance, they seem almost a little bit like the outcasts of the periodic table, with 15 of these 17 group 3 metals appearing to be exiled to the faraway F block. But in fact, these critical materials are not outcasts, they're essential. In 2019, renewable wind power supplied electricity to 3.4 million Canadian homes, and well over 100,000 electric vehicles roamed the streets of our cities. What both of these amazing green technologies has in common is that they're made possible in large part by rare earth elements. Strong permanent magnets manufactured using neodymium and dysprosium are the basis not only of electrical generators, but also compact electric motors, which is why when we're able to harvest renewable energy so that at the end of the day we can plug in those zero emissions cars, we have rare earth elements to thank. Another sector where the use of rare earths is booming is consumer tech. The microphone I'm speaking into, the hard drive that contains the software to interpret the signal, and even the speakers that deliver the signal to you are all manufactured using rare earths again. This year especially then, rare earth elements have been crucial in helping us continue on our work in safety and stay connected in spite of our physical separation. The growth of both green technology and consumer electronics is explosive, and year on year the consumption rises. And alongside this, so does the demand for the rare earth products that supply those industries. But here we do have a problem because eventually all of these products age. When a wind turbine is decommissioned or when you upgrade to the next model year of Tesla, the old rare earth containing products become waste. Researchers in this decade determined that 99% of all rare earths found in consumer products are never recycled. Take, for instance, this neodymium iron boron magnet. Shown on screen is a grade N52 magnet, which is commonly used in industry because of its high strength. In our lab, compositional analysis determined that a magnet such as this one consists of more than 20% rare earth elements by mass, and that puts even the richest ore sources to shame. What's tragic is that currently this valuable resource is almost always wasted, and it goes to landfill after just one use because of a research gap in modern recycling methods. Contemporary recycling is just too costly and too troublesome to be implemented at any kind of scale. To address the problem of rare earth waste, our research team set about developing an advanced recycling solution to extract these valuable materials from end-of-life products. We knew that in order to develop a solution that was feasible, we had to hit 3 important objectives. First, our solution had to be environmentally friendly and produce fewer emissions and less waste than contemporary techniques. Second, it had to be cheap, inexpensive enough to implement at large scale. Third, and perhaps most importantly, it had to be extremely efficient at recovering the desired materials. To achieve all 3 of these goals at the same time, we applied the novel technique of supercritical fluid extraction, so called because this method utilizes supercritical carbon dioxide as a solvent. A supercritical fluid is a state of matter at high temperature and high pressure, which combines some of the best properties of gases and liquids. Like a gas, it's highly diffusive and non-viscous, but like a liquid, it's very dense, and that makes it a good solvent. Furthermore, because carbon dioxide is cheap, abundant, inert, and safe to humans and the environment, it was the solvent of choice for our study. Now, anyone who's taken a high-quality chemistry course, such as APS 110, knows that a polar metal ion, such as a rare earth, will refuse to be dissolved by a nonpolar solvent system, such as carbon dioxide. and therefore we had to use a chelating agent to modify our extracted substances. In this case, an adduct of nitric acid and tributyl phosphate, or TBP. The purpose of adding a chelating agent is that it reacts with those charged metal ions and forms almost a protective shell around it to insulate its polarity. The nonpolar tails of the TBP are what allows the entire complex to be dissolved and transported in the supercritical phase. Now, the design of our methodology and our approach was to optimize the extraction process by tuning specific parameters in the supercritical fluid extraction process. And we used a fractional factorial approach to do this. We looked at 7 key parameters. These were temperature, pressure, and time of extraction. Temperature and pressure because they determine the density and the main properties of the supercritical phase, and time of extraction because it has a lot of bearing on the equilibrium of extraction. We looked at the ratio of the chelating agent we added versus the amount of solid samples we were extracting from, as well as the agitation rate, the acidity of the chelating agent, that is the nitric acid component in the HNO3 TBP system, as well as the addition of a methanol co-solvent, which in past experiments has been shown to improve extraction results. The results of the fractional factorial design were used to plot a linear regression with which we were to optimize the extraction process. To test our methods, we extracted from the previously mentioned neodymium magnet, which served as a model for post-consumer waste. The magnet was first demagnetized, crushed up, and pulverized, analyzed using electron microscopy and ICP-OES, extracted from, and then analyzed again. After completing the experimental matrix and performing the linear regression optimization, here are the results that we obtained. Through 2 extraction experiments performed under optimal conditions, we saw an extremely efficient extraction take place, with 94% of neodymium, 91% of praseodymium, and 97% of dysprosium recovered. This was a tremendously successful result for us. We were really happy to see it, especially considering that the method we used develops no emissions, produces 0 solid or liquid waste, and uses a minimum of energy consumption. Beyond just optimizing the extraction, our study also tried to look at some of the mechanistic aspects of how supercritical fluid extraction takes place. In terms of morphological changes, you can see that before and after extraction, these rough-looking patches you can see in my slides, those jagged particles on the surface of the magnet powder, are neodymium-rich areas of the magnet, and they all but disappear following extraction. And this suggests to us that the main mechanism of the reaction during the extraction is corrosion of the solid by the very acidic nitric acid. This finding sheds light on the mechanism of extraction, which is currently not an area that is very well understood. Our research is rather significant in that we have shown the validity of recycling post-consumer rare earth metals using the novel technique of supercritical fluid extraction. The very high extraction efficiencies that we were able to achieve, in excess of 90%, match hydrometallurgical methods, and they give us a lot of confidence in the technique that we've developed as a method for recycling post-consumer waste in the future. And they leave us really with just one more question in mind, which is, how do we scale this technology up and take it to industry so it can begin making a difference? And already our research group is tackling the questions that could make this technology into a reality. For instance, we're currently planning studies into the thermodynamics that occur in the supercritical phase during extraction. As well, we're broadening the applicability of supercritical fluid extraction, and in fact are currently running experiments on recycling post-consumer lithium-ion batteries and even performing primary extraction on ores. Our research has the potential to revolutionize the life cycle of the incredibly important rare earth materials that our society is increasingly relying on, by demonstrating a method that is unique because it uses safe, abundant, inexpensive materials. We have the potential to make a big difference by reducing the environmental impact of our rare earth usage. With our research, we're able to take what was once viewed as waste, post-consumer waste, and realize and unlock its potential as a brand new resource that could feed consumption for decades to come. Ladies and gentlemen, it's been a great pleasure speaking as your first presenter of the day, and I hope that as we go about this virtual conference looking at the remarkable and innovative work that's on display, that you don't forget about those 17 very special elements that played a big role in making it all possible, and the research that's being done to solve the end-of-life problems that they face. Thanks.
Thank you, Jilai, for your presentation. Now I would like to address the judges and ask if you have any questions. If so, can you please unmute yourselves and ask?
Sure, I can. This is Glenn Hibbert. I can ask a question. That was a really nice presentation. I've got, I guess, a two-part question here. It's question is how is your extraction efficiency calculated? And second part tied to that is how would that be affected by, let's say, the size of the particles before you do the extraction?
That's a really interesting question. Thank you, Professor Hibbert. I'll just go back to the slide on the experimental methodology here. So we performed the extraction efficiency analysis by just a mass balance. So we dissolved the raw magnet in ICP OES solution, so it was aqua regia digestion. We looked at the composition, extracted it, and took the extraction residue. So basically the magnet powder after leaching, and then saw how the composition of rare earths had decreased, and then performed a mass balance that way. So in terms of how it could be affected by the particle size, this is an extremely valid point, and because a larger particle size would lead to a mass transfer limitation there. In our case, we didn't have a way to control the powder size, so we just milled it as finely as possible. And actually, in future studies, what we're planning to do is use particle size analysis. So there's a type of instrument that will allow you to look at the distribution of particle sizes and see what the effect of that is. So we weren't able to do that for this study, but for future studies, very interesting thing to look at.
Okay, thank you.
Thank you, yeah.
Hi, I am Solmaz. Thank you for the presentation. It was beautiful. So I have a quick question. So you mentioned about methanol as a co-solvent. So how do you do that? And then how do you think that would be efficient for your purpose?
Yeah, so this is a really good question because you're wondering, why do we add the methanol? Because it's like another process step. It's another component that we would have to use. The way the methanol works is, since it has kind of like a CH3 as well as an OH, it serves to moderate the polarity of the carbon dioxide phase. So methanol will be miscible with supercritical CO2, and it helps it. Now the mechanism is not known, but it's theorized that it helps it complex better with the slightly polar metal ions that we're extracting. In terms of how we carry this out, our reactor is a batch flow reactor, so all the components were loaded in prior to extraction, and then it was pressurized with carbon dioxide.
Okay, thank you.
Yeah, thanks.